This problem begins with three masses, each about each 0.4 kilograms, and they're connected by light rods. So that means that there's a physical object holding them at this separation, 50 centimeters, 50 centimeters, 60 centimeters, 30 and 30, holding them at that separation, and the rod can push on the different masses. It must remain this rigid triangle, but the rods don't have enough mass to interfere with the problem, to influence the problem. So that's the 3.4 kilogram masses connected by light rods, triangle with these numbers. Okay. So the question is, what lateral force must be applied to the top mass to cause tangential acceleration of 2 meters per second squared to the right, I didn't say to the right, around the axis at x, perpendicular to the page. So we're imagining the triangle is sitting here. Somehow it's pinned that this point has to stay here. There's a little bearing there or something. So the whole thing goes around this point. That's the question. So the question was, what force do we have to apply? A lateral force, meaning like this. What force do we apply to get a tangential acceleration of 2 meters per second squared? Remember, tangential acceleration means sort of like the translational variables, but going around the circle. So really, the tangential acceleration will also just look like that. AT is 2 meters per second squared. So the quick temptation with this problem is to say, well, I have a force, I know the mass, 0.4 kilograms, and I need the acceleration, 2 meters per second squared, F equals ma. It must be 0.8 newtons. But it's not, because it's not really just in translational motion. It has to go around the circle, and this force not only moves this mass, but it pushes on the rod that moves that mass, which pushes on this rod that moves that mass, and blah, 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 blah. So the main first step is to realize, even though you have a mass and an acceleration and you're asked for a force of a single object, it's really still a rotational problem because it's not a single object. It's not a free object. There are other forces being applied to that object, probably rods. Once you realize that, then maybe you'll see that you're given a tangential acceleration. We need to convert that to rotational values. Convert from tangential acceleration to a rotational acceleration, and then set up the whole moment to figure out the torque it takes to make this happen, and then convert back. Right. So our strategy on this one, think through that again, is to go from tangential to rotational, and then back to tangential. Right? Because in tangential we were given AT, and we were asked to find F. Those are both sort of tangential forces, like translational properties, on the edge of a rotation. We've got to convert that, though, to alpha, and then we're going to need I, and we're going to calculate tau, and then go back to force. That's all we're going to do. Okay, so let's see. So we're given AT, and that converts directly to alpha if you know the radius of the motion of the circle, which we do. Right, so it's going around like this, a circle centered at the axis of rotation. So we really just need this. Right, that's our R, if we're going to say that AT equals alpha R, as we often do when we're going from translational to rotational. Then this R, we just got to figure out what it is with geometry. We have 5 here, we have 3 here. That always means there's a 4 there for a right triangle. 50 squared equals 30 squared plus x squared. X is 40. 25 is 9 plus 16. So in that case, then we have 2 meters per second squared equals alpha times 0.4, because it's 40 centimeters, if we want to stay in MKS units here. So right away, we know that the angular acceleration is 5 radians per second squared. That's the whole thing. All 3 masses, the little sticks hold them together, the whole thing is going around at 5 radians per second squared. So now we have alpha. Now let's get the torque. Okay, that's the next step. So for that, we go with Newton's second law for rotations. That's the only torque being applied. We're not thinking about gravity and everything. Let's not think about gravity and see if we can get the torque. Okay, so the torque equals, and the hard part of this step is to get the moment, to the moment of inertia. Fortunately, it's just 3 point particles. It's not so bad. Remember, it's the sum of all the masses. Well, there's 3 masses. There's going to be 3 terms in it. Let's do the top mass. First, it's 0.4 times 40 centimeters squared. So 0.4 kilograms times 0.4 meters squared. It's not special because the force is being applied to it. I just did it first. Anyway, it's kind of like Baker. It's not really special, but we just do it first. This one is 0.4 times 30 centimeters squared. And then this one is the same thing, 0.4 times 30 centimeters squared. It's on the other side, but remember for the moment, the direction of the side doesn't matter. There's no negative signs. Even if you put negative 30 centimeters squared, you're going to square it. It's not going to matter. Plus 4 times 0.3 squared. So that's I. That's the total moment there. Let's see if that's looking right. Yeah, it does. And then alpha is what we know, 5 radians per second squared. Okay, so if you want one intermediate number to check or to figure out where I messed up, that's 0.136 kilogram meters per second squared. Or kilogram meters squared. Right, and that's 5 radians per second squared. And let's see. In the end, then the force we get, is that it? That's, oh, no, that's the torque. Sorry. That's 0.68 newton meters. 0.68 newton meters. All right, so that's the torque we're applying to make this thing go around. And now that we have the torque, now we go back. It asks for the force. So for this, we can do the super detailed torque calculation, or we can do the simple one. Really, in this case, you can do the simple one. Torque, remember, is, let's just do it detailed. RF sine theta. All right, so R in this case is the distance from the axis to where the force is applied. It's 40 centimeters. Again, 0.4. The force is what we're looking for. The answer is 0.68. And the angle, since this is just pulling it around in circular motion, you know, it says a lateral force that won't really continue in circular motion, but we really just made it this instant. You could assume the force goes around, but at this instant it's lateral. Anyway, it's sine 90 degrees. And technically, in this case, it's minus 90. Well, let's see which is. In this case, let's get it exactly right. R is up. It's from R to F is this way. That is a clockwise 90 degrees, so the add is negative. So in this case, the force would be negative in the sense that it's pushing in the clockwise direction. But really, we would have worded this carefully and said, what's the magnitude of the force? Anyway, this is 1 either way. So it's 1.7 newtons. The magnitude of the force is 1.7 newtons. So that's one where you got to think about really what does tangential really mean? How do these tangential components really relate to the rotational components?